All right, good afternoon. Everyone doing okay? No? Okay, I wanted to start off class today. We were talking about vector functions last time, and we just got started on this. And there's one particular vector function that's going to come up quite a bit that I want to make sure everyone's comfortable with. And you may have seen this in Cal 2 if you talked about parametric equations. So here's the idea. We have a vector function. And I know some of you know this already because you answered the question last class at the end. We have a vector function, and we're going to just start with a two-dimensional vector function, which means we have two component functions. And the first component is going to be, let's just say cosine t, and the second one is sine t. And I'm going to restrict t between 0 and 2 pi. So we all need to understand what this draws, okay, what this curve looks like. All right, so what we have here, and I just did this real quick on Desmos. Let's make this 0.2. Let's let R go between, let's say, 0 and let's say 4. Okay. All right, so here's what happens. We start plugging in different values for t, all right? So like I could plug in t equals 0. If I do that, it's gonna spit out the vector. Let's see, cosine of 0 is 1, and then sine of 0 is 0. So I get a vector pointed out here, pointing at the point 1, 0. And then I keep on doing that, right? With all the values between 0 and 2 pi. And every time I do that, like let's say we plug in pi over 6, we know cosine of pi over 6 is root 3 over 2, and then sine of pi over 6 is 1/2, so we're going to be somewhere around here. And if we start doing all those points, we draw, what do we draw? The unit circle, right? We draw the unit circle. Now, the reason it's the unit circle, okay, and this is the part I want you to understand, the reason it's the unit circle is because the number in front here of the coefficients on those are 1s. If we change those to 2s, 2 cosine t, 2 sine t, what happens is we double everything, right? So the picture of that would be, let's change our radius to 2 here. You can see it got bigger, right? But still it's drawing a circle of radius 2. Y'all with me? There's something very subtle here though that we need to be aware of. Back in college algebra, is a circle a function? In college algebra, is a circle a function?
No.
No, why?
Because it fails the vertical line test.
Yeah, if we draw vertical lines, we're going to hit it more than one time, right? And so the whole idea there is that if I plug in a value for x, and we can go back to the equation of a circle. This particular circle would be this. Radius is 2, so 4. That would be the equation of this circle. Do you all agree? If I plug in a value of x, let's say I plug in 1 for x. So if I replace that x with 1, I'm going to get 1 plus y squared equals 4, and that means y squared is equal to 3, and that means y must be plus or minus root 3. So if we try and look at this as a function, then when you plug x in, right, x goes to 1, it spits out 2 different y values, root 3 and negative root 3. And that violates what it means to be a function. For a function to be a function, you have to have 1 input going to 1 output. Here we have 1 input and 2 outputs, right? Yes? However, looking at it from this new perspective of a vector function, everything's okay. Because if we start plugging in values of t, right? I have an input, t is 0, and that goes to this vector 1, 0, right? And when I start drawing all the way around, get all my points, it doesn't matter once I get down here, because this point and this point, even though it fails the vertical line test, those 2 points come from 2 different inputs, don't they? The input is t. So what we need for a function to fail is that I have an input that goes to 2 places, and these 2 points are not coming from the same input. They're coming from 2 different inputs. Does that make sense? That's critical. I mean, that is a critical thing, because now we've found a way to draw things that used to be not functions. We found a way to draw them in a way that they are functions still. Now, what happens when I come all the way around and I get to 2 pi? Well, what's it going to spit out? Cosine of 2 pi is 1 and sine of 2 pi is 0, right? So it spits out this vector again, doesn't it? Does that violate being a function?
No.
I have the same vector, don't I? I have 1, 0, 1, 0. I have the same vector came out, right? But they came from 2 different inputs, 0 and 2 pi. So even though I'm going to start drawing a circle on top of another circle on top of another circle, if I keep going, it's still a function. So we need to kind of throw away the whole idea of vertical line test, horizontal line test to test for functions, because we're no longer talking about our input being x. Our input is t. It's not on our picture. It's something in the background like a clock. Okay? Any questions on that? All right, so let's try something a little different. How about this? Another vector function. Cosine t. Let's do 4 cosine t. 0 for sine t. So now you have a vector function in 3-dimensional space, right? So you got a clock, and then this is drawing 3-dimensional vectors where your y component is always 0. But the x and the z components are the familiar number in front of cosine, number in front of sine. So shouldn't it draw a circle still? This should still draw a circle of radius what? So this number here is the radius, okay? So this should draw me a circle of radius 4, but where, right? Because it's 3-dimensional. So if this is our x plane, x, and this is our y, and this is our z axis, here our y is always 0, isn't it? So that means if we look at like the xz plane, do y'all see that that's the xz plane, the xz plane? We should be drawing a circle in that plane with a radius of 4. So it's going to be like 4 this way, 4 down, 4 back, 4 up on the z, and we should be drawing a circle within that plane. Now, if I don't restrict t, like right now I haven't restricted t, so this is basically like an infinite number of circles on top of one another. If I restrict t, like put it between, let's say, 0 and 2 pi, then I'm only going to draw 1 circle. Make sense? Okay, what if I change this number here to 2? What happens?
It's going to be shifted +2 on the y-axis?
Yeah, it's just going to move us 2 units on the y-axis. And now I have a new plane, and it's going to draw me a circle over here. So it's just kind of moving that whole circle. You're still like parallel to the xz plane. You're just moving out the y-axis 2 units. Make sense? Okay, a lot of times we want to draw circles. So I want to make sure everyone is clear with the idea of, you know, this idea of r cosine t, r sine t, and how we can use those to draw circles. It just depends on how we put them. If it's in two-dimensional space, we're going to draw a flat circle on a flat plane. But if we're in three-dimensional space, it depends on where we put these things. So another thing I could have done is something like this. 0 cosine t sine t, right? I could have defined a vector function this way. And now my x is always 0. And I'm drawing a unit circle because the coefficients are 1. And that unit circle would be in which plane?
The YZ
In
plane.
the YZ.
The YZ plane. Good. Okay. All right, any questions on that? I wanted to start with that because we're going to use this a little bit. So I just want to make sure everyone's clear on the power of r cosine theta, r sine theta, and drawing circles in three-dimensional space.
Do you have to make sure it's restricted between 0 and 2 pi?
You
That t is
don't, unless,
restricted?
you don't unless you want to just draw one circle. And that will become important later. Now, here's why. Something we did in calculus was this. Back in Cal 2. Okay, in calculus, we did this. They would give you a function f, and they would give it to you on an interval, a to b. And of course, in Cal 2, we found the area under this and all that stuff. But there was also this idea of arc length. Remember that? Arc length, where you're actually imagining taking that function off the page like a string, and then tightening it out and finding the length of that, right? That was arc length, and that you did in Cal 2. If we're going to try and do arc lengths here, which we are, then we will run into a problem if we're trying to use a vector equation. Let's go back to this one right here. If we just use this, that's going to draw us the unit circle, right? If I restrict it between 0 and 2 pi, I will draw one full revolution. And so it makes sense to talk about the arc length of that, right? Which would just be the circumference, but right, that would be, but if I went from 0 to 4 pi, well, now I've gone around twice, right? So I'm going to have a different arc length. So I guess to answer your question is, it'll all depend on the context of the problem we're working on. Sometimes we'll need to restrict the domain, sometimes we won't. Just depends. Okay. So with that, let's go back to the notes from last class. We had started talking about this. And I had gotten past all that, and I had shown you that example. And then I had gotten to this one. This is the one some of you were okay with, but now I think we can all be on board here, hopefully. And what we have is a vector function where we have a 1 in front of cosine t, a 1 in front of sine t. So since this is the x component of the vector function, and this is the y component of the vector function, it's trying to draw a unit circle, isn't it? It's trying to draw a unit circle. However, the z is changing, right? It's not held constant. So since the z is changing, we have to look at what it is. It's t over 5, which you could look at as 1/5 t. So as t grows, this thing grows, and it's linear, right? That's a linear function. So it's like you're trying to draw a circle in the xy plane, but as you draw, you start moving down the z-axis, or I should say up the z-axis. And so that's why this looks like this. We start at the bottom. We start, oh, whoa, what happened? We start at the bottom. Okay, that's t equals 0. So in the xy plane, we're trying to draw the circle, but then the z keeps on forcing us up, right, as we draw. So we get that thing that looks like a spring. Is that more clear now to everyone? Yeah. Any questions on that? So I always like to ask my students at this point what they think this would look like. We'll just do it 2-dimensional. And I'm not going to put a restriction on the, well, I'll just say t is greater than or equal to 0. How about that? Anyone have an idea?
Spiral.
A spiral. Yeah. So look, the number in front, right? Before this was just a number, wasn't it? Like if that number was 2, then it would be circle radius 2. If it was a 5, it'd be a circle of radius 5. But here, the number in front, the coefficient, is not a constant. It is actually dependent upon t. So as t gets bigger, it tries to draw me a circle with a bigger radius. But t starts at 0. So I've got to start out at 0. That's at t equals 0. I have the 0 vector. And then as t grows, I start trying to draw a circle, and with the radius that gets bigger and bigger and bigger. So it winds up doing something like this. And we start spiraling out. Make sense? What would be even cooler is if we put this in 3-dimensional space and did something with the z component, right? Because then if you do something with the z component, you can make it look like a spiral like a corkscrew kind of, right? 3-dimensionally. So it's trying to draw these circles that get bigger and bigger and bigger, but your z keeps growing. That makes sense? Okay. So you have to kind of look at this. You have to like take a real big step back and kind of think about what we're doing right now. We started the class out, we talked about 3-dimensional space. We talked about vectors. We talked about the operations we have on vectors. We talked about lines and planes, right? Distances between lines and planes and points. We talked about quadratic surfaces, what are those, hyperboloid 2 sheets, all that crap, right? And now we've gotten to the point where we say, okay, we want to talk about functions. So you want to take yourself back to, somewhere in your life when you learned about functions, right? College algebra, somewhere around there, start learning about functions. Now we're talking about vector functions. So vector functions have now been defined. And now we start trying to build the calculus in. Okay, so you have function. First thing you do in calculus once you have a function is define the limit. What do you do after the limit? What do you do after
And the derivative?
You do the derivative, and after you learn the derivative, you do
Integration.
integration. Okay, so that's what we're going to do here. We have the idea of a function. Now, what does it mean to take the limit of a function, of a vector function? Because it's different. So here we are. Here's a definition. Given a vector function, either in 2-dimensional space or in 3-dimensional space, we define the limit as shown here. The limit as t approaches a of the vector function, and this is so good, is just the limit as t approaches a of each of the component functions. So there's nothing new here. To take the limit of a vector function, you're going to just be taking a limit of each of the components. That's it. That's great because there's no new thing we have to learn. And if we have 3 components, we'll do a limit of each one. So let's just do an example. See, here's the thing, and I don't want us to lose sight of this. Why, in Cal 1, we do derivatives and applications and stuff, and in Cal 2, we do integration and all that. I mean, why isn't that enough? Why do we have to do vector calculus? Like, why does this part of the subject exist, right? Well, I'll tell you, I mean, it's exactly because of what we just started this class with. Everything in Cal 1 and 2 had to be a function. It had to pass the vertical line test, right? And in the real world, shit just doesn't work that way, right? When you talk about, first of all, we live in 3-dimensional space, right? So flat sheets of paper only take us so far. And then if you have some object like a rocket moving or something like that, the way it moves through space, it's perfect for a vector function, right? We need some way of defining these things. So really all of this part of calculus is leading us to real world stuff. That's what it is. You can only do so much with a function in Cal 1 and 2 on a flat sheet of paper. You can only do so much with that. Okay, back to this. So we want to find, given this vector function, it's a three-dimensional vector function, we want to find the limit as t goes to 0. So all you have to do here, all you have to do here is take each component and just take the limit as t goes to 0. That's it. Limits are nice because, like I said, there's nothing new. Like, it's not like I have to teach you some new rule about limits for vector functions. As long as you can take limits like you did in Cal 1, you'll be okay. All right, so here we go. I haven't called on people lately. So let's go with Daisy. Is Daisy here? I'm crushed. My feelings are crushed. Okay. Abi?
Yes, I'm here.
How's it going?
Good.
Good. Okay, so I'm going to ask you for some limits here and put you on the spot. Okay, so when we do a limit, I'll just remind everyone, whenever we do a limit, we always try direct substitution first, right? So we just like let t be 0, plug it in, see what you get. So what do you get here for this first limit?
1.
1. Okay, cosine 0 is 1. And notice that my answer is a vector. Do y'all see that? My answer is going to be a vector. All right, how about the next one? Abi?
Is it undefined?
So you get sine of 0, 0 divided by 0, you get 0 over 0. Okay, so when we have 0 over 0, that's a problem, so we have to do something, right?
Right.
Do you recognize it or no?
It's been, honestly, it's been a while, so
Okay.
I'm not picking it up
That's
yet.
okay. That's okay. How about Lorraine?
Yes.
How do you feel about that second limit?
That's going to be 0.
So you're getting 0 on top, 0 on the bottom, right?
Yeah.
And that's 0?
Correct.
So when you take a limit, you get 0 over 0, that's just 0? Sure.
Yeah, I think it's, yeah, because sine of 0 is like, should be 0, and then plug in 0 for t on the bottom, 0.
So if you get 0 over 0, isn't division by 0 undefined? So look, Lorraine, hold on. Let me go around. Let me ask some more people. I'm not telling you you're wrong. I'm just making sure you're sure. Fabiola? Are you here? No? Okay. Adam, what do you think?
We're gonna have to do L'Hopital.
Okay, so look,
Oh,
0 over 0 in a limit is a problem. It's an indeterminate form. You cannot conclude anything when you get 0 over 0. So Adam is bringing up L'Hopital's rule, which you either learn in Cal 1 or in Cal 2. So Adam, how does L'Hopital's rule work?
So if it's 0 over 0 or infinity over infinity, you would take the derivative of both of them,
Okay,
and then just plug t equals 0 back into it.
okay, so using L'Hopital's rule, which I always use in L and I circle it, even though a lot of books use an H, what you do is you rerun the limit, but with the derivative of the top over the derivative of the bottom. So derivative of sine of t is cosine t, derivative of t is 1. And now, Adam, when you run that limit, what do you get?
Would be 1.
1. Okay, so it's 1. So a little side note here for everyone. You're going to have to do limits, all right? So if you don't remember limits from Cal 1, you're going to need to go back because We're going to be using L'Hopital's rule and all the indeterminate forms. There's an entire like section on this stuff, sections plural. So you need to know how to attack each one of these and get yourself up to speed. All right. Right. What about the last one? Let's see, Terrence, how do you feel about the last one?
Not really great.
Okay, so as t goes to 0, right? As t goes to 0, each of the 0, so anything
Should
to
be
the
1.
0 should be 1. 1 minus 1.
0.
So we get 0 on top, and then on the bottom, t is going to 0, we get 0 on the bottom,
Yeah.
right?
So L'Hopital's again, right?
L'Hopital, yeah. So what's the derivative of the top?
It's still e to the t, right?
Yep, just e to the t, yeah. And on the bottom, derivative of t is
1.
1. Okay, so now run the limit again. Let t go to 0.
So then it's going to be 1, right?
1, yep. Okay, so we got 1. Good. So the limit of this vector function is a vector 1, 1, 1. Now let's just take a quick step back and just understand what we're doing here. If I asked you right here at the beginning, if I asked you, hey, what is R of 0, everyone? What happens when you plug 0 into this vector function? When you plug 0 in, you would be undefined here. These two components would be undefined. So this vector function is not defined at 0, but here's what we can tell you. We can tell you that as you get closer and closer to 0, the vector function will be spitting out vectors that are getting closer and closer to 1, 1, 1. Now, it's never gonna, you can't plug 0 in, but in the limit, this is where it's headed. Any questions? Okay. So we talked about limits in calculus, and after we talked about limits, we talked about continuity. And back in Cal 1, continuity meant basically that you could draw the graph without picking up your pencil. Like that's the real like easy kind of way to think about continuity. So for us, it's the same exact definition. If we have a vector function, whether it be 2-dimensional or 3-dimensional, to say that it's continuous at a point A means that the limit of that vector function is equal to the value of the function at A. That's the exact same definition from Cal 1, except instead of having a vector function here, we had just like f of x or something. So the limit at A equals the function's value. There's really not a whole lot more to discuss in that. It's just, that's just a definition. All right, so I want in this one I want to see if somebody could tell me what this thing looks like. Can anyone just look at that vector function and right away be able to tell me like generally what this looks like?
Can I say it out loud?
Sure.
Looks like the equation of a line.
It is. That is exactly the equation of a line. So when we were studying lines, thank you, Daniel. When we were doing lines earlier, we had the vector equation of a line. That was it right there, right? So what we did is we said this was like an initial point, and then this was our direction vector. And every single time we deal with a line, we always wind up getting like something in here that's linear, something in here that's linear. In other words, linear in t, the variable t, and something linear. Anytime you have linear, linear, linear in each of the components, well, it's going to draw a line. All right. So I guess we actually were studying vector functions before we even started technically studying vector functions. We did one example and that was it. So that example is just about like recognition. Okay, recognition. All right, so now what we want to do is we want to find a vector function. I say find the vector function that will draw a line segment that goes from one point to the other. So this example that I'm about to do is, I wouldn't expect that you could just do this right now without any instruction. I'm going to show you how to do this, and that way you know now from here on out, if you ever need to come up with a vector function that will draw just a line segment from one point to the other, here's the way you do it, okay? The first thing you do is you figure out which point you're going to start with, okay? Here's the point you're going to start with, because we're going from there to the other one. We're going to let that, we're going to let that be our R naught in our good old vector equation of a line. This was our vector equation of a line. So that's going to be our R naught, always the starting point. And then I'm going to need to get V. And to get V, I come up with a vector that is going from here to here. And we've done that so many times now that I think Jorge can tell us what that vector, direction vector V should be. No, Jorge? I guess Jorge's not going to tell us. All right, how about Donald?
Yes.
Yeah, so what's the vector that goes from this point to this point?
It's gonna be -8,
-8,
2,
2,
and -12.
-12. Good. Okay. Got it, everyone? Good, good. So R naught, sorry, I didn't put what R naught is. R naught is this vector 359. So now we just put it all together. So we say, okay, RT should be the R naught, which, so didn't we do stuff like this already? Like this isn't new, right? This is not new. What's new is going to be the next step when I put them together. So I'm gonna put these all together. I'm going to get 3 minus 8t. Putting the x components together. 5 plus 2t, putting the y components together. And then 9 minus 12t, that's our z components together. So right now, this is the vector equation. That's the vector function that draws me the entire line. Okay, this draws me the entire line, and that's not what I want. I want the line segment, only the part of the line that goes from 359 to -573. So this is where things get super easy. All you have to do is say, okay, restrict t between 0 and 1. Now I have a little asterisk, you know, those little disclaimers that you never read at the bottom of a form. I have a little disclaimer here. Well, let me say it this way. It will always be restricting t between 0 and 1, always, as long as you do it the way I just showed you to do it. In other words, you always have to make R naught the starting point. Oh, as long as you make R naught your starting point, and you make V the vector that goes from the starting point to the other point, then I promise you that if you restrict t between 0 and 1, this will work. If you try and be, you know, creative and use R naught to be the endpoint instead of this one, it's not going to work. It's going to draw you a different part of the line. It's not going to draw you that line segment. Okay, so just be careful with that. The book does some other stuff. I don't like the way the book does it, so this is the way I present it. All right. Any questions? All right, now this problem is going to be weird. I'm going to let you think about it for a minute. Okay, I want you to think about it first. So I'm just going to let you think for about 2 minutes about this. Are you all ready to start talking about this? Does anybody have any questions before I start about this, about what's being asked? All right, so how about Juan? Are you here, Juan? No Juan, okay. How about Maribel? I see Maribel. Are you there?
No, not really.
You're not there?
No,
You always sound so far away.
I know.
So I just had a question, Maribel, for you.
Okay.
Do you have any sort of concept as to what, sorry, let me get this in here. Do you have any sort of concept as to what this is? Like, what does that look like geometrically? And think about what we did last class.
No.
No?
No.
Is that what you said?
Yeah.
Okay, so last class we talked about quadratic surfaces. We talked about, oh, you need to see how many variables there are,
Mhm.
how many of them are squared. Do we have any variables that are free that aren't being used? Remember all that?
Mhm.
Okay. So if you've got two of your variables squared equals a number,
Mhm.
this is going to be a cylinder. Now it says it here, right, that these are
Mhm.
cylinders.
Mhm.
So this cylinder, which axis does it open along? So is this like, does this thing go along the z-axis? Does it come out the x-axis? Does it come out the y-axis? Do you know?
The z-axis.
Z, right? Because the z isn't here.
Mhm.
Okay. So here's what I know. I've got a cylinder that's like vertical like this, right? And it has a radius of 3.
Mhm.
Now, Maribel, how about this second one? Still a cylinder, right?
Mhm.
Which axis does it go down?
The x-axis.
The x-axis. So it's like this. Like that, right? Something like that.
Mhm.
And it has a smaller radius. It has a radius of 2. So what this question is asking us to do, and Maribel, you're good. You can mute. What this is asking us to do is for us to find a vector function. Vector functions draw curves, right? Vector functions draw curves. That's what I said last class. Vector functions don't draw surfaces, they draw curves. So we need to find a vector function that represents the intersection of these cylinders. So we need to find a vector function that somehow draws where these things hit each other. Do y'all see that that's rather complicated when you think about it? Because here's what we have. We have two cylinders hitting each other like this. And we are trying to find that curve right there where they hit each other, right? And those curves are not just simple circles. In fact, let me take the cylinders out of here so they don't distract you. Do you see that the curves that we have, like, I guess from one angle, they do look like circles, but if you look at them from the side, do you see that they're not like perfect circles? You see that? So this seems like a pretty challenging problem, doesn't it? Like initially, seems like it'd be difficult for us to do this. Yeah? It's going to turn out that it's not that hard. All right. So let's think about it from this perspective. Can we draw this with the vector function? So that is just x squared plus y squared equals 9 is basically a circle of radius 3, right? And that is going to be, that's basically this cylinder, right? This cylinder, it's just a bunch of circles like this. That's all it is. Yes. So could I draw that with a vector function? Sure, I could draw that. How would I draw it? What would I need? What would I need? I need a circle in the XY plane, right? With a radius of 3. So anyone want to volunteer? Tell me what the components would need to be? What the X component would have to be?
Can I take a shot?
Go for it.
So I'm gonna guess that our X has to be 3 sine of T,
Why
or
is it-
sorry, cosine.
Okay, yeah. Now, it turns out you could use sine, but let's stick to what we've been doing.
I
3
didn't think it
cosine?
really mattered, so I kind of just said one. Let's see, we're on our Y component now, then it's going to be 3 sine of T.
3 sine T. Okay, good. Hold on for a second, Daniel. Good. Does everyone see that that is going to draw us a circle in the XY plane right now of radius 3? Do y'all see that? But we know that when we're doing this, okay, so it's like, you know what? I have this backwards. I have it the other way. Yeah, I can do it. So we're drawing circles, right? But we need to be able to fluctuate our Z. See, this is not good. I did it the other way around. Ours looks like this. Okay, so what Daniel's done is he's going to draw a circle in the XY plane. So we have to, these are reversed. So just imagine that this is the bigger cylinder and this is the smaller one, okay? Daniel's given us a way to draw these circles in the XY plane, but he has not told us anything about what's happening with the Z. And we need the Z to fluctuate, right? To go up and down a little bit. You all with me? But Daniel's allowed us to at least draw those circles of radius 3. Okay, do you want to keep going, Daniel? That would be more than I expected of you at this point.
Well, I'm just trying to draw the big cylinder, right?
Well, that's what you've done. So far, that would draw a circle of radius 3 in the XY plane.
But
That's
we
what
needed to, if we're trying to draw the cylinder, it needs to cover the entire Z plane, right?
Do you want to draw the whole cylinder?
Well, if we're just, I thought we were trying to find the vector function of x squared plus y squared equals 9.
Okay, so you will never be able to draw the cylinder with the vector function. You'll
Okay.
never be able to, because vector functions only draw curves. Later on, we will be able to draw surfaces with vector functions, but not yet. Not yet. We would have to introduce another variable, which we're not allowed to do at this point, but later we will. So right now, I want everyone to just understand that if we're going to define a vector function, it's only going to draw a curve. And what you have so far drawn is the part of this intersection that creates the circle-ish part when you look at it this way. We still have not accounted for the up and down. So can I assist? I'm just going to assist a little bit here.
Go for it, my man.
Okay, so look, separate thought. Take this equation right here. See, don't we want to know what the Z needs to be, right? Like the X is going to be 3 cosine T. The Y is going to be 3 sine T. The only thing we don't know is that, what is our Z going to be? But it must be on the intersection of both of these cylinders, which means whatever Z we put here must also satisfy this equation, right? Because that's the other cylinder that we have to be on. So how about we take this equation and solve it for Z? Let's solve it for Z. If we solve that for Z, we'll get Z squared equals 4 minus Y squared. And then Z must be plus or minus the square root of 4 minus Y squared. Right? However, do we know what Y is?
3 sine of T.
It's 3 sine T. See, because we've already Daniel defined X and Y for us. So here's where we're at. We're pretty much there. Okay. Daniel said, I'm going to do 3 cosine T. That's going to draw me part of the circle. 3 sine T is going to draw me the other one. And then the z we got from this equation, I'm going to put plus or minus, but I'll fix that in a second. And then 4 minus the y squared, but y is this, 3 sine t. So this should be 4 minus 3 sine t squared. There. That's it. This is the vector function. Well, actually, aren't there two vector functions here? Because one of we have a plus and a minus. Y'all see that? So we have two vector functions, and guess what? We shouldn't we? I mean, these are two different curves. We need to be able to draw each one of them. So one of them we draw when we have the plus, and the other one we draw when we have the minus. Do you all follow that? So this should be our vector function that should draw this, and we should let t go between 0 and 2 pi, because that'll draw me the full circle, the full revolution. Or will it? This is where we have an issue. Is it right to make that your domain? Can we plug in every number between 0 and 2 pi? Maybe I'll do it this way to help you. 3 cosine t, 3 sine t. And then I'm just going to use the positive one, square root of 4 minus 9 sine squared t. So I went ahead and squared the 3 sine t, and made 9 sine squared t. Do y'all see that there are some values of t that we could plug in where this number would be bigger than 4, and then we would get negative here? So you would now have to go solve this in order to get the domain. You'd have to ask yourself, when is 4 minus 9 sine squared t greater than or equal to 0? So you'd have to solve that. Now, we're not going to. I'm not going to. I'm just trying to stress to you that this domain is not correct. You would have to actually solve this quadratic trigonometric inequality to figure out your restrictions on t. And I don't want us getting bogged down on that right now. So, okay, let's see if we can just back up and figure out what we did here again. We were given two cylinders. We said, hey, draw me the curve that shows their intersection. So Daniel said, all right, let's take this right here and try and draw at least a circle of radius 3 in the XY plane. So he put that there, and I said, great, all we need to know is z. But if we're going to be on the intersection of these two, then it has to satisfy this. So we solve for z and then replace the y with this, right? Okay, I want to do something different now. Same problem. I just want to approach it slightly different. I'm going to draw this first, okay? So if I draw that, that's a circle of radius what?
2.
2 in which plane?
In the x plane.
In the
Oh, I'm sorry. In the YZ plane.
The YZ plane. So I need the y component to be 2 cosine t. I need the z component to be 2 sine t. Do y'all see that that's going to draw me a circle of radius 2 in the YZ plane, right? What I don't know is what x should be. And to figure out x, guess what I'm going to do?
Solve for y.
Solve for
x with the other equation.
Solve for x from this equation. See, this just draws me a circle of radius 2. So I know that this will always satisfy that equation. Always. Because I generated it from that. But to simultaneously be on the intersection, I must satisfy this equation. So I solve that for x because that's the thing I don't know. And when I do that, I get x is equal to plus or minus the square root of 9 minus y squared. And then I can replace y with what?
With 2 cosine t.
2 cosine t. So minus 2 cosine t squared. So we get square root of 9 minus 4 cosine squared t. That's what x should be. So again, I'm going to have two different curves. I put that in here. The positive root, that'll give me one of the curves, and then I do the negative root, and that'll give me the other curve. But look at this. Which of these is better? I want you to understand, we did this two different ways, right? Two different ways. And when we did it, they should draw the same curves, right? They should draw, even though they look completely different, they should draw the same curves. Which one of them is better? And why?
This new one would be better because of the domain restriction for t.
Yeah, good, very good. So look, if we look at this one, look at this under here. 9 minus 4 cosine squared t. We need that to be bigger than or equal to 0, don't we? Well, that would mean that we need, let me just do some basic algebra here. I'm going to move the negative 4 cosine squared t to the other side. And I'm going to divide by 4. 9 divided by 4 is what? 2.25. Do y'all agree? 2.25 is greater than or equal to cosine squared t. Do y'all agree that that's always true? I mean, cosine is bounded, right? Cosine is always between -1 and 1. So if you square it, that's going to still be a number between -1 and 1. And that means that'll always be less than 2.25. So my domain restrictions here, there are none. If I let t just go, it can be anything. It'll just keep drawing me these things over and over and over, right? Whereas with the other one, I have to be a little more careful about my choice of t because, see, on this one, if we do the same thing and divide, 4 divided by 9 equals sine squared t. Well, see, sorry, bigger than or equal to, bigger than or equal to. This is not always going to be true. There are some values that I could plug in here for t that would make this bigger than 4/9. And so I have problems with my domain here. And all I did to do it the other way was, instead of choosing this one and drawing that one first and figuring out what z was, we chose this one, drew that one, and then figured out what x was. So there was nothing, I mean, there's nothing wrong in the way that Daniel suggested we do this, okay? It worked. I don't think any of us could have foreseen the domain issues we were gonna have, all right? But we have them, so. Okay, any questions on those, on that example?
So when you get a messy domain, do you just do it the other way?
No,
Or
just
try it the other way?
Then you have to actually go find that domain. Like if you stick with this or the other one, you got to tell me the domain restriction here. And I
Right.
think I did it. I didn't show you, but yeah, here's the domain restriction. T's got to be between -41.8 degrees and 41.8 degrees, or between 138.9 degrees and 221.8 degrees. That's our domain restriction. Let me actually convince you that it does draw this. Here it is. Those are the vectors that will be drawn. So if I start letting t vary in the vector function, that's the first curve it draws. And if I let t go on the other one, it draws the bottom half. Okay, that's just to convince you that this does work, but that's our domain restriction for it. Okay. So why would this be useful? Why in the world would we ever want to come up with a vector equation that represents the intersection of two cylinders? Just for fun. I don't know, maybe your company makes metal, metal piping for commercial use for, what do you call it? Like water treatment plants or something like that, where you have pipes coming together, right? And maybe your company wants to save money, right? So they're trying to figure out, because you have to weld these together, right? Like you have to weld these pipes together. So it'd be nice to know how much material that is, right? How much welding is that? I've got to pay my welder by the hour, or maybe I pay them by linear foot or something, right? So it would be nice if I knew the length of that blue arc. Like how much is that, right? So we'd find the arc length of that later, maybe, right? I'm just thinking just off the top of my head. That seems like maybe why I'd want to know that, right? Okay, we're moving on.
Oh, so real quick, I have a question.
Yep.
So it also includes everything like in between the two circles, right? Or not circles, but like weird shapes. It includes everything between it, right?
Nope,
Just the weird shapes?
it's just the blue. That's all it
Okay.
is. Mm-hmm.
Even though it says
Yeah.
intersections?
It's the blue curve lives on both cylinders, right? It lives on their intersection. You can look at it this way. The blue curve is made up of all of the points that are on the intersection of both of those cylinders, right? It's just all the points that are on both cylinders at the same time. If I pick this point, that point's on this bigger cylinder, but it's not on the smaller one, right? The curve is the points that they both have in common. It's their intersection. Does that answer the question, or?
Yeah, I see.
Yeah, if you were to pick a point on the inside here, then if we looked at it from here, I know that's got to clear that out, but that point in here would not be on both cylinders. It would be maybe on one of them, but not on both. All right. So, once you come up with a vector function like we just did, once you come up with these, drawing them is really tough, but computers make things nice for us. So we can use computers to sketch vector functions. I've already done it for you. But here are two really kind of cool examples. They're just neat. Okay, there's nothing too special about them, but they're just kind of cool examples. This is an example of what's called a toroidal spiral. So you all know what a torus is? A torus is a donut, okay? A torus is a donut. This is a vector function that basically does a spiral around a donut. And so it looks like that, okay? A toroidal spiral. And the vector function for that one is right here. It's hard for you to see. This is the x component. It's 4 plus sine of 20t, that whole thing times cosine of t. And then the y component is 4 plus sine of 2t times sine of t. And then the z component is cosine 20t. If you plot that, this is what you get if you graph it. So kind of cool. The next one, you don't need to know this. I'm just showing you, okay? The next one is called a trefoil knot. And what makes this one cool, it's just like, I think about it as like a bee flying through the air or something, or a fly, right? Just flying through the air. If you were to connect all these together, right, the flight path, this actually ties a knot into itself. So it creates a knot. And the vector function for that one is up here. It's not important, but here it is. Okay. So yeah, and just remember what's happening is once we have the vector function, we start t, right? T starts maybe at 0, and then we just start plugging in values of t, and it draws vectors. And when you put all those vectors together, you get you get the path. You get the path through space. All right, moving on. Derivatives. I have more good news. If you want to take the derivative of a vector function, either two-dimensional or three-dimensional, then all you have to do is take the derivative of each of the component functions separately. Okay. Nice. We know how to take derivatives, so there's nothing new to learn here. Now, what does the derivative mean? That's something different. What did the derivative of a function mean back in Cal 1? If I
The
say,
rate at
hey,
which-
here's the function. Go ahead.
I was gonna say that the derivative was the rate at which the function is changing.
Yeah, at some point, it's like the slope of the tangent line, isn't it? I mean, that's what it was in Cal 1. We would start with a function, and then we would pick some point, let's say x equals a. We go to that point, and from there we defined, well, we talked about the tangent line, and the slope of that tangent line was equal to the derivative of that function at a. So if this function is the function f, the slope of that tangent line is going to be the derivative of that function at a. So the rate of change of the function at a, right? That's what it meant back then. What does it mean for us now? Well, first of all, when you take the derivative of a vector function, you get a new vector function, okay? And so it creates a vector, and that vector should be tangent to the curve at some point, just like this was, okay? We're going to get a vector that's tangent. So let's see it in action. So here's an example of a vector function. It's down on the bottom here. You'll see that vector function. It's the vector function r of t equals t sine t, t cosine t. That's the one I was telling you about earlier with the spiral, right? That was the spiral one. So let's take a look at what the tangent vector looks like. So as I move along here, I have two things labeled here. I have r of t, which would be the vector that actually draws me that point, okay? So r of t is this vector that draws me the point. And then r prime of t is the vector that is tangent to the curve at that point. So that's the geometric relationship we have. Here's r of t, r prime is tangent vector. And as we move along, I want you all to notice what's happening with that vector. In the beginning, look at r prime. Obviously, it's changing directions, isn't it? What about its length? Does the length look like it's changing? Or no? Hard to say.
It's slightly increasing.
That's definitely bigger, right? That vector r prime is longer than that r prime, yes? So remember, vectors have direction and length, right? Direction and length. We're back in Cal 1, when we had a slope of a tangent line, it just had a slope. I mean, just the slope was the slope and that was it. But here, because it's a vector, it has direction and length. All right, so here's what I'd like for you to do. I'll give you a moment here. I give you a vector function. That's this one right here, the one we just had. I would like for you to find the vector that is tangent to that vector function, which means you have to take derivative, and then evaluate it pi over 2. Then see if you can find the vector equation of the line. And I'm going to put you in breakout groups for about, I don't know, 5-10 minutes. See if y'all can, you have to pull some stuff that we've already talked about. See if y'all can pull it together and get an answer. The group that gets the answer right will get 2 points bonus on the whatever mini exams y'all turned in, all right? Okay, so I'm going to randomly assign you into groups. See what y'all can get done in 10 minutes. Hopefully you'll get some people who want to play in your group. What do y'all want, 3 to 4 people, or do you want 4 to 5? Bigger or smaller group?
Bigger?
Bigger?
Okay, we'll go 4 to 5. There we go. Okay, I'll check back. I'll pull everyone back in 10 minutes. If you need to copy the problem down, go ahead. Okay, I think everyone should be back now. All right, so we had 3 breakout rooms. I already took note of who was in which room. So does any group have an answer?
Yes.
We got part of an answer.
Okay, so Damien, your group, your room 3. Okay, anyone
Yes.
room 1 or 2?
I think we have an answer.
Yeah, we have an answer.
Group 1 does.
Okay, and how about room 2?
Yeah, we do as well.
Okay, so let's do this. Let's go with room 1. Can room 1 tell me the vector that is tangent to that curve at t equals pi over 2? What's the vector?
Okay, so for the, okay, for that second part right there,
No, the first part. Well, okay, so find the derivative. You want to tell me the derivative?
let's see, make sure I got
I
this.
don't-
See, how about here? Yeah, because we put that in right there. I'm not sure that we got that. I'm saying it the right way. I've got some scribbles here. So group, correct me if I start going off the reservation here. I have pi over, I have 1, right? Yeah, 1 and then negative pi over 2.
I forgot to tell y'all, if you get it wrong, I take away 10 points. I'm kidding, I'm kidding. Okay, so you're saying that the vector that is tangent to that curve at t equals pi over 2 is the vector 1 negative pi over 2. Okay, so that's room 1. How about room 2 and 3? Y'all agree or no?
Yeah.
Yes.
Yes? Okay, so we're gonna go with yes. And if you got that correct, then that means y'all got that correct. Right?
Yes, okay, yes.
Well, most likely. There is a way to make a mistake and still get the right answer sometimes. Okay, do any of the groups have the third one? Third part of this? The actual vector equation of the line.
The x component would be pi over 2 plus t. And then the y would be negative pi over 2 times t.
Okay, what room was that? That was
Room 2.
2.
that's room 2. Okay, room 1 or 3, did y'all get that far?
Room
No.
1 got the same answer
Okay,
as the pi over 2 plus t, and then negative pi, except we just said negative pi over 2 times t. Yes.
okay, so look, I'm gonna assume that everyone's okay with the first 2. And I just wanna talk about how the third one is arrived, how we arrive at that. We're trying to find the vector equation of a line, right? And so what we need to do that is we need an R naught plus T V, right? So V, in this case, V would be the direction vector, right? Of the line. But the direction vector should be the tangent vector because that tells us which way the line is supposed to be going. So that should be this. The R naught is any point on the line. And so how do you get that?
Point we are.
You have to plug in a t
Into what?
into the r regular r of t.
Yeah, so the idea here is that we have a curve, right? So I showed you this picture before. I'm going to erase this. I showed you this before, that what we have is we have this blue curve, right? And we're trying to find the vector equation of the line that is tangent to this curve at a certain point in time. So the dotted line is what we're looking for. The red vector is the direction vector of that line. All we need is a point. And to get a point, we can pick any point on the line, but how about the point that's also on the curve, right? That would make the most sense. So all we need to do is figure out what that vector is. And that's just plugging the point in time into the regular vector function. So that means we want to plug in pi over 2 into this. So if you plug pi over 2 into that, you'll get your R naught. And then you just add the two together. That's how you get that final answer. Okay, so here's what I'm going to do. I'm going to give everybody credit for this today. All right, everyone who was in a room, everyone's going to get bonus. I've already marked it down. Okay, so if you weren't in a room, you don't get bonus. All righty, what time we got? 20 minutes still? All right, we still have a lot to do in this section. All right, now unit tangent vectors. So we just saw that when we have a vector function, this blue curve, that we can find that red vector by just taking the derivative, right? But notice again that that red vector changes length as we move along, right? It changes, depends on the function, but it does change length. So sometimes what's important to us is not the length of the vector, just the direction. And so what we do is we find what's called the unit tangent vector, okay? And what it is this. Do you see, just like we had before, we have r prime of t, that's the red vector. The unit tangent vector, which we represent with a capital T of t, that is the vector that is parallel to the red vector, pointed in the same direction though, and always has a length of 1. So as you move, notice that purple vector always maintains the length of 1. And we know how to make unit vectors. We've done unit vectors before. Remember how to make the length of a vector 1? What do?
You divide by its magnitude?
Yeah, you just divide it by its magnitude, by its own length. So that will be our definition for a unit tangent vector. If r prime of t is the r prime of t is a vector function, then r prime of t is a vector, so we can always find the unit vector in the same direction. This is called the unit tangent vector. And so all you do is you take the derivative vector and you divide it by its own length. Okay, and that will create this new thing called the unit tangent vector. So for the one that we just did, right? For the one that we just did, if we wanted to find capital T of pi over 2, all we would have to do is take r prime of pi over 2, right? What was that vector again? It was it 1 negative pi over 2?
Yeah, 1 negative pi over 2.
Okay, so to find capital T of pi over 2, all we do is take that vector and divide it by its own length, so the magnitude of itself. So that means you take that vector 1 negative pi over 2 and you divide it by the square root of 1 squared plus negative pi over 2 squared. And that's just going to be some weird number, right? So here's what it'll turn out to be. A vector where the 1 and the negative pi over 2 were the things that were there, and you're dividing each of those by this length, which is the square root of 1 plus pi squared over 4. All I'm doing is just squaring each one of these. And I'm just going to leave it like this. It's fine. So here's what I can tell you about this vector. It points in the same direction as this vector. But if you measure how long it is, it has a length of 1. Questions?
When would we need to use this?
Okay. So later on, I'm just going to think of one example. Later on, we're going to be talking about something called flux, which is like a measurement of like electromagnetic flow through a patch of space. And when we measure that flow, it's basically going to be a bunch of vectors going through think of it as like water flowing through a net. And so what we'll be interested in is not the length of these vectors. We're just going to be interested in their direction. And so the unit tangent vector will be useful to us because the fact that it has a length of 1 keeps all of our computations easier. Just makes it a lot better when the length is 1. So all we do is what we call normalize those vectors. We just make them all a unit length. And that way, when we calculate that flux, it'll be an easier computation. I guess that's one way I could explain it. It's the direction that matters, not the length, later in certain applications.
So
All right.
fluid dynamics kind of stuff.
Yep, yep. We don't get that till the very end though of this class. All right, so blah blah blah. I think that one I can leave for you. It's basically the same problem, but now you have a 3-dimensional vector function. So you're gonna take the derivative, and then you're gonna figure out what that derivative is at a certain point. The tricky part to this problem is that, you know, on this one that we did just now, that I asked you to find the vector that's tangent to the curve and I gave you what t is. Right, I told you, hey, t is pi over 2. Tell me what's going on here. On this problem, I don't give you t. What I give you is a point on that curve. But you still need to know what t is in order to answer the question. So how would you figure out what t is?
T is pi over 2, just because of the z coordinate.
Yeah, I mean, it's kind of obvious in this, but see, if this point lives on that curve, then there's some value of t that when you plug in that value of t, you get 0 here, you get 1 here, and you get pi over 2 here. But if the z component is t itself, then it's hopefully obvious that t must be pi over 2 then. Right? And then you can check sine of pi over 2 is 1, and cosine of pi over 2 is 0, 2 times 0 is 0. So this right here tells you that t is pi over 2. And then you just do the same thing you just did in groups. So I'm going to let you do that one on your own. Not right now, but ooh, what's this? Okay, so this is that's just that problem. It's 3-dimensional now. So you can see the tangent vector on this 3-dimensional curve. Right? So that's the beauty of the tangent vector, is that we are no longer stuck on a flat sheet of paper, right? We can move this into 3-dimensional space now. One way to look at a tangent vector is, you know, let's say that this is, you know, some object moving through space, and then all of a sudden right here at this point, it loses all, like, let's say it had a rocket on it and it's got, you know, it's got some aileron, so it's like pointing itself in some direction, right? And it's trying to travel through space. This tangent vector would represent what happened if at some instant in time it lost all power and control over where it's going. It would just keep traveling in a straight line in the direction it was going at that instant, which would be the tangent vector. Okay. All right, remember in Cal 1 we had second derivatives? We have second derivatives here. So the second derivative of a vector function is just the derivative of the first derivative. All right, so now we have a definition of what's called a smooth vector function. Do y'all remember what the second derivative told us in Cal 1? I know the first derivative tells you where you're going up and down, right? If your first derivative was positive, you're going up. First derivative was negative, you're going down. What did the second derivative tell us in Cal 1?
Maximum and minimum.
You could use it to help you find maximum, but there was something about if the second derivative was positive that tells you something about the shape.
The concave.
Concave up or concave down, right? That's in Cal 1 though. Now we're talking about vector functions. So when it comes to the second derivative tells you something about this thing called smoothness. All right. Well, it'll help us with it. Let's just look at the definition first. A vector function, okay, a vector function R of t given on some interval I is called smooth. All right. If the first derivative is continuous, which means when you take the first derivative, it's defined. And if the derivative is not 0. Okay, wait a minute, what? In order to be smooth, to be called smooth, your first derivative can't be 0. If your first derivative is 0, then the vector function is not smooth. That's kind of weird because, again, if you think back to Cal 1, right here at this point, let's say at this point A, if this is the function f, do you all agree that at this point it looks like the derivative of that function at A is 0? The first derivative here is 0 because the slope of the tangent line is 0. But this is a smooth curve, isn't it? Like it's nice and smooth, no jagged edges or anything like that. So the first derivative being 0 back in Cal 1 didn't tell us anything about smoothness. But with vector functions, the first derivative does tell us about smoothness. And if the first derivative is ever 0, then it's not smooth. I mean, sorry, if the first derivative, is 0, then we will say it's not smooth. If it's not 0, then we can say that it is smooth. And then when I say 0, I mean the 0 vector. So let's see an example, okay? Look at this right here. Is this a smooth function for all t? All right, well, let's check. Let's take the derivative real quick. What's the derivative of this vector function? Okay, so I need to take derivative cosine squared t, so I have to do chain rule. 2 comes out, 2 cosine t, times derivative cosine, which is negative sine t. So that should be the derivative of the first component, and then derivative of the second component is 4t cubed. Y'all with me? I'm just going to clean this up. This is going to be negative 2. I'm going to just rearrange it. Sine t cosine t. 4t cubed. So the question is this smooth? Well, what we need for this to be smooth is we need this first derivative to never be the 0 vector. So can somebody think of a value of t that might make that thing 0, the 0 vector? Go ahead.
0.
0, right? Look, at t equals 0, what happens? R prime of t equals, well, the 0 vector. Which means that we are not smooth at 0, right? We're not smooth at 0. Is that the only place that we would get the 0 vector?
Pi would also give it to you, right?
At pi?
And
Pi would
pi?
make this 0, but would it make this 0? No, it would just make one of them 0. So to be the 0 vector, we need them both to be 0, right? So the only way we're ever getting the 0 vector out is if this one is 0, and that only happens when t is 0. So it looks like it's smooth everywhere except at 0. Do you all understand that? Okay, let's take a look at this curve, all right? I'm going to graph it for us, and we're going to see what's happening at t equals 0 and see why we can't call it smooth. Here it is. I'm going to slow that down. So look at this blue curve, all right? I want to go to t is 0. Okay, at t is 0, we're right here. It's hard to see it, but do y'all see we're right here? And that's like back in Cal 1, we call that like a cusp or something, right? But we can't talk about it that way because now we're vector functions and it's different. But there's something interesting happening here, right? This curve is not smooth there. Got this little pointy edge to the curve. So look at the tangent, okay? This red vector that you're looking at here is the tangent vector. I want you to look at what happens to that vector as we start getting closer and closer to that little thing, that little cusp. We've got a vector, look at its length. Look what's happening. Boom, and then it gets there, and then now it's the 0 vector, and then watch what happens. Boom, look at that. Went from there to there, right? changed directions rapidly. Went from going to the right, basically going to the left in like an instant. And that's what causes the non-smoothness. Everything else is a nice slow transition as it turns. Not so much here at this little cusp. It's a quick, rapid, violent changing of direction of the derivative. Or the tangent vector. Okay. All right, differentiation rules, just things that you should know about taking derivatives of vector functions. I'll just talk through these real quick because this will be the last thing we do today. If you ever want to take the derivative of two vector functions being added, you can do them individually. That's great news, yes? And if that's subtraction, it works also. Okay, plus or minus becomes plus or minus. All right, if you ever want to take the derivative of a constant times a vector function, you can just take the derivative of the vector function and then bring the constant along for the ride. So that's same thing from calculus. The next one is a little different. This is the derivative of a function with a vector function. So let me give you an example of this. If I want to take the derivative with respect to time of sine of t times the vector function t cosine t. So this is multiplication, right? This is sine of t times this vector function. So here's our vector function. This is our u of t. And this right here is our scalar function f of t. So if you want to take the derivative of this, what you can do, does anyone recognize this?
It looks like
Product rule, right?
It's like the product rule.
yeah,
Exactly.
product rule. I forgot the name.
Yep, it's like the product rule. You do the derivative of the scalar function times the vector function plus the scalar function times the derivative of the vector function. So that's a product rule. And then look at the next one. Two vector functions dotted together. If you want their derivative, what can you do? Isn't that a product rule again, kind of? But it's not multiply, it's a dot product. So it's u prime dot v plus v prime dot u. And cross product is the same thing. It's like a product rule. And then the last one is chain rule. If you have a vector function inside, you plug a scalar, then you're going to do chain rule. We'll do examples of these. We're out of time, but we're not done with this section. We still have more to do here. So we need to do that example right there, really cool. And then we're going to do some applications. And then we're going to talk about, after applications, we're going to do integration. And then we'll be done. So that next part will probably take us, I don't know, 30 minutes of next class. And then we'll be done with this section. And once we're done with this section, we move into the next section. Let's see where we are in our calendar here. So today is the 10th. So we were supposed to try and finish this up today. We didn't quite get there. But look at what's on the docket. Arc length. Okay, so that's coming up real soon. Arc length and then something called curvature, which we didn't have in Cal 1. And then we start talking about functions of several variables and we start getting into the next chapter. So we are almost at the end of chapter 10. Chapter 10 ends right there. So we have one more section, chapter 10, then we move to the next topic. All right.
When is this mini exam due? This second one?
So I sent an email out last week, right? So you have a set of problems that I gave you that covers lines and planes, right? That one is due on the 18th, which is going to be next Thursday? Did I say 18th?
Yeah, he said 18th.
I did. Okay, so it's due on the 18th, but you're going to submit that in a Dropbox. So that's when it's due. And then
I don't know if you said it was due on the 18th the last time. I thought you were talking about literally right now. As in for the first mini exam.
The first mini exam is already past due.
Yeah.
Yeah, that one's gone. The one on lines and planes is due on the 18th. And then I sent the second mini exam, which was not lines and planes. I sent the second one in an email last time, and that's due on the 22nd. Just check your inbox, your Canvas inbox. It should all be there. And you can go if you need to go. In Canvas under course files, I've started to put all the mini exams in there. So in case, you know, you need to get to them, you don't have to go through your email. They're right there. Any other questions? Man, what is this? Is this week 4? Are we done with week 4 of this class now?
About week 4, yep.
It seems like things are going by so fast. I don't know. Maybe not for you, but for me it does. All right, keep up with your homework.
All right, sir. Thank you.
Thank you, sir.
Good one.